Hey guys, welcome back. It's time to get our overview of Chapter 2. Chapter 2 is about how things appear in the sky and the models that we use to try to understand sort of what's really going on. So let's begin with the ancient Greek astronomers. Obviously, in ancient times, there were no telescopes. The technology had not been developed, and people had to observe everything through just the human eye. And so, but given the limitations of their technology, these guys did amazing work. So, first of all, the early catalogs of stars enumerated the stars' brightnesses. They were only able to see stars, as I said, that are visible to the naked eye, and so the brightest stars they gave the number 1. Those are first-class stars, you could say. There are, in fact, we know now, stars much brighter than that. Class 0 or even -1. But based on what they were seeing at the time, they labeled the stars with 1 through 6. So the stars that are just barely at the limits of human vision are 6th magnitude stars. Stars that are the brightest stars in the sky are 1st magnitude stars. Now, with the technology we have today, we can actually measure the amount of energy per square centimeter coming from any part of the sky, and we can determine how much energy flux is arriving at the Earth from any given star. And so we know that the ratio of the most energetic star to the stars that are called magnitude 6, which are just at the limits of human vision, the ratio of those energy fluxes is about 100 to 1. So that's 5 magnitudes of difference, according to the ancient magnitude scale, corresponds to a factor of 100. So that converts to a logarithmic scale that we use, the so-called magnitude system. And so if you go to the astronomy calculator that I cooked up and pointed out the other day, there are a couple of formulas there: difference in magnitude from flux ratio and flux ratio from magnitude difference. So if you know the difference in magnitude of two stars, you can use this calculator to calculate the flux ratio. If you know the flux ratio, you can use this calculator to calculate the magnitude difference. The formula is actually given there. The difference in magnitudes is 2.5 times the logarithm of the flux ratio. And if you go the other way around, the flux ratio is 100 to the difference in magnitudes divided by 5. That's because if you have a difference of magnitude of 5, that gives you a flux ratio of 100. That works out, but it's an exponential scale. All right, very good. So let's get back to our overview here. The brightness and the flux, factor of 100, those are all the things I just said, basically. Flux is just a word that means amount of energy crossing a unit area per unit time, and it corresponds roughly to our notion of brightness. Okay? So let's see. There are groups of stars in the sky that the ancients gave names. We call them constellations or sometimes asterisms. Constellations are the official groupings that have been accepted for many, many years. Asterisms are sort of more casual groupings, like the Big Dipper is an asterism. It's actually part of the constellation. Let's see, hang on a second. Ursa Major, I guess. So, but those groups of stars called constellations, I think there are 48 or 50 or something like that of them, you're probably familiar with. Things like Pegasus and Gemini and Orion and so on. Now the thing is, the ancients named all the stars, and they used Greek names because they were Greek people. And so you'll often see stars that belong to constellations given names according to the Greek alphabet. So there's Alpha Centauri. Alpha Centauri is the brightest star in the Centauri constellation, and so on. And Beta and Gamma and Delta are less and less and less bright. Epsilon would be the 5th brightest star in the constellation, and so on. So when you're looking at star names, if you see it's a Greek name, then you can guess it's probably fairly bright. It's among the stars that are visible with the naked eye. And depending on the letter that precedes the name, you can tell if it's the brightest in that group or the next brightest, and so on. Does that make sense? Good. The other thing is we have a coordinate system that we use to describe the location of the stars. So, and the exercise for this week, the project that we're going to be doing this week, involves learning about the celestial coordinates at the same time we're learning about terrestrial coordinates. So I won't go over that again. I pointed it out in the last overview, but basically there's this idea of longitude and latitude on the surface of the Earth. There's a corresponding idea of right ascension and declination, which are the celestial coordinates. And along with that comes the notion of sidereal time, and that's the absolute time measured relative to the Earth pointing in certain directions in space. So when the south, let's put it this way, when you're facing directly south and the zero of right ascension crosses overhead, which is roughly in the constellation Aries, I believe, your sidereal time is 0. An hour later, it's 1 hour of right ascension after that. 2 hours of right ascension is 2 hours later, and so on. So right ascension is actually measured in hour angle. 24 hours is one full rotation of the Earth. Whereas declination corresponds almost directly to latitude. Declination just says how far above the celestial equator are you, at what angle. 90 degrees would be pointing along the celestial pole. 0 degrees would be pointing out along the celestial equator. And hopefully that will become more clear after you work through the first project. If you have questions about that, please don't hesitate to ask. The last thing I want to talk about in the little overview is the notion of sun and moon cycles. The reason the stars appear to rise in the east and set in the west is because the Earth is spinning on its axis. But not only that, the Earth also orbits the sun, so the location of the sun relative to the background stars depends on the time of year. One time of year the sun is in one constellation, and a different time of year it's in a different constellation. Let's see if we can see if I can pull up. If I go to the textbook, you'll see the chapter contents are listed there, and if I click on the apparent motion of the sun, there's a nice picture. So as the Earth goes around the sun, you can see, like right here, let me go ahead and zoom in there. Right here, the Earth, this is on January 1st, at noon you're looking right at the sun, and if you could see it, you'd see Sagittarius, but of course you can't because the sun blocks out the sky. But at midnight, you're looking straight up at Gemini. So you get a sense of how it turns out that different stars are visible different times of year. If you wait till March 1st, then if you look straight up at midnight, you see the constellation Leo, and so on. Okay. So, but not only that, the moon also orbits the Earth. And so a lot of the questions in the homework this week are about how to interpret what's going on with the moon. And I just wanted to point out that I put a link on ACE to this Lunar Phase Simulator. And this is a handy guide because it lets you see what's actually going on here. The moon is between the sun and the Earth in this picture. At noon, looking straight up, you'd see what's called a new moon. In other words, the illuminated side of the moon is opposite you, so you can't really see it. That's a so-called new moon. I'm going to run the animation slowly here so you can see what happens. But if you start the thing going, the Earth goes around once, it turns once on its axis, and in the time it takes to turn around once, it'll be 1 day later. And at this point, the moon now has moved, well, it's approximately a 30th of the way around. It turns out to be about 13 degrees in one night. And you can see that now it's just beginning a slight crescent phase. In other words, you can just see the sunlight striking the surface and peeking around the side. If I wait another day, then you'll see that the crescent phase is getting more pronounced. So if I wait till noon on the next day, now you can see barely a crescent moon happening there. Now I want to point out something. If I show time tick marks, you can see sunrise is when you as an observer come around and just see the sun at the beginning of the day. This is noon when you're looking straight up and the sun is straight overhead. This is sunset when you're just about to pass into the shadow. And then midnight, of course, is when you're over here. So if you look at this particular guy, let's go back a few hours. At sunrise, the moon wasn't even up yet. The moon is first visible. Here it is. The moon, if you look in this picture, the moon is just barely visible, following the sun through the sky, and it's in a crescent phase that's growing. If I then go ahead and run the animation, you can see that throughout the day the moon is following the sun, but as time goes on, the next day the moon is farther behind the sun, and the crescent phase has grown larger. The next day the moon is even farther behind the sun. It doesn't rise until much later, and as the sun sets, you can see the moon is actually fairly high in the sky. The sun is set because I'm now in the shadow, but the moon is still visible to me because it hasn't set yet. And now the crescent phase is getting quite pronounced. Let me go ahead and speed up the animation here so you can see it a little better. And I'm going to stop the animation when the moon reaches a first quarter phase. That means at sunset it's directly overhead. Let's go back just a couple hours. There we go. So the moon is now directly overhead at sunset. It looks like a half moon. It's gone through its crescent phase. It's beginning to start into its gibbous phase. The gibbous phase is from from first quarter to full. Okay? And so anyway, I don't have to dwell on this, I don't suppose, but you can use this both in your moon observation project and in working the homework to figure out what's going on at different times. One of the homework problems is when does the moon rise when it's at third quarter, something like that. So you can use this animation to help solve those kinds of questions or sort out those kinds of questions. All right, I hope that helps. Very good. Let's solar and lunar eclipses. I can go back to this guy and point out something about that. Now, a solar eclipse is when the moon gets between the sun and the earth. So a solar eclipse would happen when the moon is like this. We're going to have a solar eclipse actually coming up in August. I think it's August 17th. It doesn't happen every month, because the moon's orbit is at an angle and it has to be lined up. The orbit has to be in the same plane as the Earth at the same time it's new in order to have an eclipse, and that happens relatively rarely. Now, a lunar eclipse is when the moon is on the opposite side, when the shadow of the Earth falls on the moon. That's a different situation where the moon, that happens only during a full moon, and in that case, the moon becomes blocked out, and you can't see it for a little while because of the shadow of the Earth. And that's basically the idea. So I think that's most of it from Chapter 2. I'll put up an overview of Chapter 3 here in just a little bit. If you guys have any questions about any of this or any of the homework, please don't hesitate to post a question to the forum and we'll get it answered. Talk to you guys soon.